Today we're going to go over examples of undamped free vibration of a single degree of freedom system. In the first example, we have an undamped mass spring system in a horizontal plane, and we were given the equation of motion, which is mx double dot plus kx equals 0. M is the mass, and k is the stiffness, and x is the displacement. In the first part, we're asked to show a free body diagram with inclusion of the inertial forces, and we have to explain why the moment of inertial forces is 0 in this case. As you can see in this sketch, we have the spring, which is represented by K, and we have M, and then x1 is the first displacement and x2 is the second displacement. Now we draw the free body diagram. So we're gonna have M, and then mx double dot, and then kx. And then the second part of this question is explaining why the moment of inertial forces is 0. So the moment of inertial forces is 0 because we don't have moment acting on the arm. The second part of this question is asking to obtain the equation of motion by imposing the equilibrium of the block. So to do this problem, we have to use this equation. So displacement of the spring, which equals to negative kx d of s, and then same thing for the stiffness, which equals to negative mx double dot. So adding these equations together, we're gonna get negative kx t of s plus mx double dot d of s equals 0. And we factor out d of x, negative d of s, we will be left with negative kx plus mx double dot equals to 0. This part is neglectable, and then our equation of motion will be, sorry, this is plus because we factor out the negative, so our equation of motion will be mx double dot plus kx equals 0. Moving on to the third part, we're asked what is the principle of virtual displacement. So the principle of virtual displacement states that in equilibrium, the virtual work of the forces applied to a system is zero. In equilibrium, the virtual work of the forces applied to a system is a zero. And we're also asked, write the equation of motion by using the principle of virtual displacement. So to do that problem, we're gonna have to use the equation of the kinetic energy, which is T equals 1/2 mx dot squared. And then we also have to use the equation of potential energy, which is 1/2 equals kx squared. So u plus t equals constant. So the sum of kinetic energy and potential energy is equals equals a constant. And to continue solving this problem, we have to take the derivative of both equations, the kinetic energy and the potential energy. So we're gonna have d over dx of 1/2 mx dot squared plus the derivative of 1/2 kx squared. Okay, so we take 1/2 m outside, and the derivative of x dot is x dot. Squared is just multiplying this times 2, and then x dot x double dot. So these two cancel each other. We're gonna be left with mx dot x double dot plus, same thing here, the two cancel each other, is dot, the derivative of that. So we're gonna have kx and then x dot. and then we set that equal to 0. Now we factor out x dot. We're gonna be left with mx double dot plus kx equals 0. We ignore this part, so mx double dot plus kx equals 0 is the equation of motion using the principle of virtual displacement. And then finally, we have to explain the principle of conservation of energy. So the principle of conservation of energy is simply if no work is done by an external force, the kinetic and potential energy is constant, which is basically what we just did. U plus T equals constant. U is the potential energy and T is the kinetic energy. And this is it for the first example.